Okay.
No, it's
Go
butterfly.
in front of the camera. Really good.
Oh no, I'm not done.
Not the butterfly?
No, this is butterfly. This is breaststroke.
Oh, breaststroke is like
the
this.
camera that way you can.
Oh no, like
So
they don't
it's
get this for
consuming.
free.
Okay, let's see.
No, because it's a pelvic thrust for the fly.
Okay.
Oh,
So
okay.
it's like that.
Oh, interesting.
You're welcome.
So I was doing it incorrectly. I have to thrust my
You
pelvis.
gotta give a little pelvic thrust for us, sir.
Oh, okay, like dolphins. And dolphins swim like that.
No, but I think Mr. Science is gonna do
Hey, you
it.
got a future, man. You got a future.
It's not in swimming.
That's one way to pay for it. Alright, anyways. So, that was our break from calculus.
Alright.
You can use that move, okay? Throw it into one of your officer tryout dances or something.
I can teach you this.
He can teach you the pelvic thrust. Alright, anyway, so what's
What just happened?
Get out of here.
I'm so glad something I ruined
We
everything.
went from there to pelvic thrusting.
somebody did it in second block, but they didn't do it like that.
They didn't put the pelvic thrust.
They didn't. It was interesting.
Unwise.
I'm gonna have to bring that up to him. He's probably not a good swimmer.
Was it
So, what would this point be called right here? A cusp. Very good. So this isn't a point of inflection. Why? Because this is concave down and this is also concave down. So did it change concavity? No. So it is not a point of inflection, but it is called a cusp. So that's where the graph has a what? A sharp turn, okay. It had a really quick and sharp turn. So quickly that at that moment in time, what kind of a tangent line am I going to have right there? Okay? So it's going to happen so quickly, but at that instant there should be a what? Vertical tangent line. Okay, so we kind of already answered the two questions that I'm going to ask next. Is it continuous at that value? Yes, it is continuous, but is it differentiable? No. Okay, so let's see if we get those two answers by proving it. Right, so the first one, let's prove continuity. Is it defined at 0? What is the value? 2. Does the limit exist at 0? The limit as x approaches 0 from the left equals what? 2, and the limit as x approaches 0 from the right also equals what? 2. Therefore, we can say the limit as x approaches 0 from both sides equals 2. The third step is that to show that those two are equal. Are they equal? Yes. So f of 0 equals the limit as x approaches 0 of f of x. Therefore, we can say that the function is continuous at x equals 0. Good? Remember doing all this a while back? Proving continuity? Do you remember IVT? What was IVT? Intermediate value theorem. What had to be true for intermediate value theorem to apply? Had to be continuous? F of A could not equal F of B? And the y value that they're giving you had to be in between, not A and B, F of A and F of B, right? The two y values that they gave you, right? So therefore, that means that there had to be IVT applied, right? IVT guarantees some x value such that when you put it into the function, gives you that y value that they were saying. Remember that one? Yeah? Okay. We'll review it later. Alright, so now let's check the differentiability. Again, we said that we were going to have a what? Vertical tangent line right there. Alright, so let's prove it. So what's the derivative of f? And the derivative real quick. Let's go, hurry up. Power rule. 2/3 x to the negative 1/3. Okay? And we could rewrite that as 2 over 3 cube root of x. And we're going to evaluate it at 0. So we get 2 over 3 cube root of 0. So that just gives us 2 over 0, which we know is undefined. Therefore, we can say what we said earlier just by looking at the graph, that the function is not differentiable at x equals 0 because f prime of 0 is undefined. So what happened in this one? Was this one continuous? Yes. But, again, it was what? Not differentiable. So again, I gave you 2 examples there where something was continuous but not differentiable. So I think we kind of solidified the idea that continuity does not imply differentiability. Okay? Cool? Which is what the next question is asking. Right? What did we learn? Where is the function not differentiable at? At an endpoint? At a point of inflection? At a cusp? Okay? How about if I had something that was not continuous? Like let's say I had a jump discontinuity. Would it be differentiable here? Yes? It would be differentiable there?
No.
No? Why not?
Because you can see that there's a whole bunch, there's a point at the same line. I don't know.
Is it continuous? No.
It's not differentiable.
I don't know, that's what I'm asking.
No, it
No,
isn't.
it is.
It isn't.
It is? Or it isn't?
It isn't.
It's not.
It isn't.
Wow.
You don't think so?
No, it's at the endpoint.
It's like an endpoint?
It has to be
It has to be continuous to be
Yes.
differentiable?
No, that
Isn't
was
that
one.
what it is here?
No, we just said that.
Is that what we
No,
just
it's not.
said? We didn't say that.
the opposite.
We said that it doesn't have to be, that if it's continuous, it doesn't mean that it's differentiable. But we didn't say that for it to be differentiable, it had to be continuous or it didn't have to be. But my notes do? Ah, you cheater, you looked on the other side. Alright, so before we look at this section, okay, that was a good conversation.
Busting our brain.
Okay? So let's answer this part up here. Does continuity imply differentiability? So because something is continuous, does that mean it's automatically guaranteed to be differentiable? No, we just discovered that. We showed 2 examples, right? So let's write that down. Continuity does not imply differentiability. So what could I use to prove that? What were the 2 cases that we saw where it was continuous but it was not differentiable? So because at a point of inflection or at a cusp, right? The graph is continuous but not differentiable. So those are kind of examples that are counterexamples to the idea that if something is continuous, it's automatically differentiable. It's not always true. Okay, you gotta be careful. Good? Now the other question is, does differentiability imply continuity? And that one I'm going to tell you that it is true. Okay, if something is differentiable, It must be continuous. So differentiability does imply continuity. Yo, totally massacred. Good? Good? Alright, so in order for something to be differentiable, it has to be continuous. Okay? Because there are places where it's not differentiable. Right? We kind of discovered some of those places. And I wrote it down here for you. So a function is not differentiable at some value if any of the following are true. So the first thing that can throw out throw out differentiability is if the function is not continuous. So if you see somewhere it's not continuous, boom, automatically you can say no, it's not differentiable there. So what are places where functions are not continuous at? So holes, okay. Where else? Vertical asymptotes, okay. Where else? Okay, you want me to put jumps? Okay, jumps. Where else? Where do the math purists believe that a function is not continuous?
Endpoint.
At an endpoint. Right? Okay, so those are all places where something would not be continuous. Do I need to draw examples for you? No? If you need examples, you can draw them here. That's why I left that space. Okay, the other place is if the graph has a what? A cusp, which is a sharp turn. Okay, so for example, the absolute value graph, right? Or the cube root of something squared. Bless you.
Thank you.
Or let's say I have a line and then I have a parabola. Okay? So anywhere that there is a sharp turn in the graph, it would not be differentiable. Understand? Yeah? And the last place is anytime I have a what? Vertical tangent line. So some places where I have vertical tangent lines, bless you, are at what? Points of inflection. Do I also have vertical tangent lines at cusp? Yes. Okay? So in general, anytime if you were to draw a tangent line and you were to end up with a vertical one at that particular point, you could say that it is not differential. Pretty good? We're almost done, I promise. These last 3 examples and we're done. Okay? Try to bear with me. I'm sorry. It was a long lesson today. Imagine if we would have done it all.
Everybody did a second brush.
No, I didn't. I stopped right there. They're not that hardcore. Imagine. Alright, so let's look at these 3 and let's see if we can sketch the graphs of these functions and be able to determine where they are not differentiable. That's what they're asking you to do. The first one is asking you to graph that absolute value function. So you do need to know your mother functions and know what they look like in order to draw other ones. Okay, because you won't have a calculator for some parts of the test. And you will have to do things like this. So what does the absolute value graph look like? It's a V, right? Now this isn't the original absolute value graph. It was transformed. It moved. How did it move? 3 down and 2 to the left. Very good. So 2 to the left and 1, 2, 3. That's where my vertex is, and it should be opening up because there was no reflections. Okay? So it says, by visual inspection, determine any points at which it is not differentiable. So where would it not be differentiable at? At the cusp, right? So we know that that's a cusp. So tell me where it's not differentiable. F of x is not differentiable at x equals what? -2, because there's a cusp is not a good enough, vertical tangent line is not, because f prime of x is undefined. That's a good enough justification. Okay? Can't just say because there's a cusp. You gotta be careful. Good? Alright, let's see if we can graph this guy. Let's sketch the graph of that function. What kind of function is that? Who's that baby's mama? Parabola, right? Quadratic. Okay? Except what happened to it? It's gonna go one up, 3 to the right, and it has a reflection because of the negative. So reflected about what axis? The x-axis. So it's gonna flip over the x, move 3 to the right, and 1 up, right? Cool? So let's do that. 1, 2, 3, 1 up, and you always perform the reflection first, guys. Okay? Unless otherwise specified. So unless in the problem they tell you move it this way, move it that way, then reflect it, then you follow that order. If they don't, you always perform the reflections first and then the movements. Okay? Or else you will get a completely different graph. Because if I moved it and then I reflect it, it's going to flip to the bottom quadrant. Do you understand? Alright, anyway, so let's look at this guy. Where is it not differentiable at? X equals